learning, right? So we have introduced the unsupervised learning. We understood what is the difference, this unsupervised learning, when compared with the supervised learning models, right? And also we have understood uh, the unsupervised learning is also called in terms of competitive networks, right? We have seen various competitive networks in terms of learning. Okay, so whether it is the simple networks such as MaxNet, then Mexican Hat Network, Hamming Network, then self-organizing maps such as coherent self-organizing map, then learning vector quantization networks such as LVQ network, then you have adaptive resonance theory networks such as ARPANET. These are the various networks that were introduced on the other day. So as I've said, basically we are going to call them as competitive networks in the sense when you look at the nodes. When I say nodes, essentially we are talking about the output nodes. Of course, see, so far actually you are looking at the network topology as there is a input layer, there is a hidden layer, there is an output layer kind of a thing. This is the topology you are seeing. But from now onwards, you don't see such type of layered, multiple layered topologies like this. Okay, you may see some input and as well as output. Okay, so it is the topology of the network varies from what so far we have learned. So in that way, when you look at the computative networks, the nodes at the final layer, okay, so there would be one particular neuron or some associated group of neurons that would be providing the activation, and those nodes are only called as winner nodes. Okay, because you are calling it as a competitive network. When there is a competition, obviously there is a concept called winner. Okay, so those nodes who are identified as the winner nodes only would provide the activation. Now the point is, before we proceed to the one particular network, how do I say that winner node? So take an example of your the supervised networks. What we were actually doing is we were providing the input, then calculating the activation. Then once activation is getting propagated in the forward direction, finally at the output layer, we are calculating the output, right? And then checking with the targets based upon the kind of learning, either you propagate the error back towards the hidden layers. So that's what we are actually doing. There is nothing like concept called a winner node. Here we are saying that the network is a competitive network, and it is competitive network because there is a winner node or a group of winner nodes. Okay, before we call group of winner nodes a little later, let us take there is only one node, which is the winner node. Now, the point is, how do you determine that a particular node in the layer, okay, now let us even think that there is an output layer. Now, one particular neuron or one particular node in the output layer is how you are going to say that it is the winner node. So for that, there are two ways of identifying a winner. Number one, calculate the distance, okay, Euclidean distance between your input vector and the weight vectors. Okay, so that means what? You submit an input x1, and for every neuron, obviously there is a corresponding weight vector for that particular neuron. So that means imagine the neuron is having about 5 connections. Obviously every connection is having a weight. So that corresponding weights of the node would constitute the weight vector. So what is that we are going to calculate is we are going to identify the distance between the Euclidean distance between the input vector and every node weight. So the input vector and every node's weight vector, the distance is going to be the Euclidean distance. You are going to calculate the Euclidean distance, and the node with the smallest distance is identified as the winner node. That is one way of identifying which is the winner node. Remember, we would be discussing this in the when we are talking about the algorithms. But then you have to keep this approach back in your mind when you are viewing the algorithm. So we are going to identify the winner node in the network. Remember, the network is a computative network. So there would be one neuron which is going to be declared as the winner. And the way you are going to declare the winner is based upon the two approaches. One, verify the distance with the input vector and corresponding neurons weight vector and identify which node is the smallest, having the smallest distance. That is one approach. The second approach is find the dot product. Okay, find the dot product between input vector and the weight vector. Okay, so when you do that, the maximum value that the node, whichever is the node that is producing the maximum value, would be the winner node. Remember, when you are verifying the the Euclidean distance between the vectors and identifying the winner, it is the minimum distance. When you are calculating the dot product, the node which is producing the maximum value, when you calculate the dot product between the input vector and the node's weight vector, when you do that, whatever the node that is having the maximum value would be the winner. Now tell me, what is the dot product? When you do the dot product between the input vector and weight vector, what is that you are actually calculating? Can somebody tell me? You are listening.
Net input.
Exactly. So essentially, right from the beginning, we were keep doing this activity only. We calculate the net input. How do you calculate the net input? Essentially by calculating the dot product between the input vector and the weight vector of the node, you are going to get the net input. So when I say I'm going to decide the, excuse me, I'm going to decide the winner node based upon the net input, what is that I need to understand is that the activation that is coming out of the neuron is essentially your input, right? So that means the activation function, what you are going to apply here is the ramp function, right? So when you are having a positive net input, that would be passed out. If you are having the the negative input, then you will be getting a 0. So now anyway, coming back to the calculation of the winner node, either you verify the winner node by calculating the Euclidean distance or by checking the dot product. So when you are saying that based upon the dot product you are doing it, essentially what you are doing is calculating the net input. And remember, the activation that is coming out of the neuron is net input, means you are actually applying the ramp function. So that's the typical activation function that needs to be considered for the network. Now we proceed and to the next one typical network, and the network is called MaxNet. Okay, so we see now first network of computative networks called MaxNet. So essentially it is a simple network, very simple network, and it is also as we discussed, it works on computation, right? So it looks at the computation and it works. Then the network is fully connected network. It is also having symmetric interconnections symmetric interconnections. The point is, when you look at the associative memory, there also you have the symmetric interconnections. But the point here is that there you don't have the self loops, but here you have self loops. Now with this, if you look at the network architecture, let me put the diagram here in the screen. This is how your typical network architecture looks. So you are able to see the diagram, right? Okay. Okay. So this is how a typical network looks. So imagine you have about m neurons. So there is m neurons. Okay. So you have y1. Remember, we are calling the neurons as y1, y2, y3, say yi, and say ym. Now, if you notice, these are all interconnected. So one is connected with the rest of the other nodes in the network. And not only that, it is also connected itself, which is not there actually in the associative memory models, right? So you have, the corresponding connection weight is 1. And if you notice, the network has some, the connection weight between the various connections, which is fixed connection weight. Okay, I hope you guys remember yesterday we said there is no learning for the first category of networks. When we say there is no learning, weights are fixed and also they are predetermined. Now look at the case here. Imagine you have some delta, you have all the connections are having fixed, connection weights. And in addition to that, you can also notice the connection weight is in the negative. That means these are all inhibitory connections. Okay, these are all inhibitory connections. Okay, so we discussed about yeah. Now what happened? You present the network input. Input is presented to the network and allow the network to converge. Okay, so allow the network to converge. So once you fix your the nodes and the node connections and the corresponding weights, what you do, you present the input to the network and allow the network to converge. Remember, when you are presenting the input, the initial input, obviously what we are going to get as an output is the initial output. So that means at step 1, when you are iterating, when you are performing, your y's would be typically your x, right? So that means when you present the input, whatever that at a particular stage 0, if I say step 0, whatever the input you are getting, that if you pass on, that would be the output at step 1. So but now onwards, you are going to verify what is the input. Say, take an example, y1 node is having input from itself and also from the rest of the other connections. If you notice, the y1 node is having the connections not only to itself but also from the rest of the nodes. So in that way, you are going to calculate activation to that particular net input to this particular node with the help of all other nodes. Output from the all other nodes is going to be provided as an input to the node I. Say, take an example yi. So the node will be receiving the input from itself and also from the rest of the nodes. Okay. Now then, when we say network is allowed to converge, what happens when during the convergence? once the network is converged, what is that is going to happen is, except one node, okay, except one node, which is the winner node. This particular node is the winner node. Okay, except that one node, the rest of the nodes activation attains 0. So except one node, rest of the nodes get 0 activation, and the node with the positive activation is the winner node. Okay, the node with the positive activation is the winner. Okay, and there is a criteria here, one important criteria, that while choosing the connection weights, the fixed predetermined connection weight, is that the delta is supposed to be 0 less than delta less than 1 by m. So that means you have m is the total number of nodes in the network, the delta or epsilon, whatever is the connection weight, which is the predetermined weight which you are going to fix, that should be satisfying the condition that it is the positive value and less than 1 by m, where m is the number of nodes. Okay, so this condition has to be kept in mind. And also y out, if you know, that means the activation function is f of y in, which is in fact is the input. Okay, I will write it in the next slide. Otherwise, I'll keep the the algorithm. So have a look at the algorithm. That in one way it is better. Are you able to see the slide 3 with the algorithm?
Yes, sir.
Yeah. Let's focus on the algorithm. So if you see the MaxNet algorithm, so you are going to have the size of the network, wherein which m is the number of nodes. And remember, actually, the other day as we discussed, a typical use case of two clusters or two categories, the output nodes, what we have seen in the previous slide, you can even regard them as the y1, y2, y3, y4 and all. These are all the cluster nodes also. They can be regarded even as the cluster nodes. Okay, so the reason why your m size network is having y1 to ym number of nodes. That's what we have seen in the architecture. And all the interconnection links have the inhibitory predetermined weight, which is lambda. Okay, and of course, it is, since it is inhibitory weight, it is not excitatory weight, and hence it is not positive, and hence it is negative. And all self loops are given as the weight 1. Now then what you do, you present the network with the input x. So obviously x is having m features. Okay, so x1 to xm. Remember, when we proceed further for a self-organizing network, we see with a different set of inputs. But for now, for a Mexican hat, for a MaxNet, we are seeing the input size is also the total number of cluster units, or the total number of units in the output layer, or m is the size. Then what you do, you present the input to the cluster units. When you present the input for the first step, as I've said in the previous slide, for the initial step, that means step 0, what we are going to do is we are going to just simply pass whatever the input to the output units. Okay, that's the reason why your net input is xi for step 0. Remember, this is for step 0. That means the first step. For the rest of the steps, what you are going to do is different. Okay, but for step 1, once you have this input assigned to the neurons, what we are going to do is verify the activation. As I've said, activation is through the ramp function, where you are going to simply pass the positive net input that you get to the neuron. Okay, so that's the reason why this is your net input. The positive net input you are going to just simply pass. So f of y in, that means the f of net is the net if net is positive. Otherwise, it is 0. Once you calculate the activation for every node in the cluster, that means at the output, what you are going to do is you are going to check whether I have reached the stopping condition. How do you know that whether I have reached a stopping condition? The condition is that if all units except the winner node are having the 0 activation. Okay, so all the rest of the units should be 0. That means they are not the winner nodes. So there is only one node which is the winner node. Again, I repeat, for now I am saying there is only one node. Imagine when we move to the Mexican hat, you may be having more than one node also as the winner nodes. Okay, such type of network is called not only competitive network but also cooperative network. Okay, competition, there is only one winner. When the network is with cooperation, it's not only one node but also multiple nodes be the winners. Anyway, we will come to that a little later. But now, as I said, there is only one winner, and hence what we are doing, the stopping condition we are verifying is that we are checking if all the units in the layer Y or the cluster units have to be exhibiting the 0 activation except one node. That particular node with the positive activation, we are going to call it as the winner node and then stop the network iteration. But for every iteration, look at the step 0. We just passed the input to the nodes. But when you move to the iterations, what is that I am going to give as an input? When you move to the iterations, you see the step 3, what we are doing is the net input is the previous output minus the weights and outputs from the rest of the nodes. Okay. Hope you also remember the network architecture. So if you see the network architecture, Y1 is having activation coming in from rest of the other nodes, right? So that's what is getting captured here. Y out, that means output of Y1. Say, imagine we are calculating for first node. The previous step output of Y1 minus the predetermined weight of epsilon or lambda, of course, which is common for all the connections. And that's the reason why you have minus lambda into Y out of all the rest of the nodes, summation over Y out. Remember, J is not equal to I. If it is J is equal to I, already you have the condition Y out here. So for the rest of the nodes, whatever is the output that is coming in, that gets multiplied with the corresponding connection weight. Of course, you have only one weight. Imagine if you have multiple weights, obviously you would have been written, you would have written it as W1 into whatever is the node plus W2 into whatever is that node, etc. But since your W is common, it is how your net input to each cluster unit is calculated. Then what you do, once you calculate the net input, again you go and check the activation and check the stopping condition. We reach the stopping condition, yes, otherwise no. So proceed further. Okay, this is how your MaxNet clustering algorithm or MaxNet competitive network algorithm works. Is that clear? Oh. Is that clear here?
Yes, sir.
Okay.
Yes,
I
sir.
think, okay, morning you must have been tired, and maybe after lunch you guys are having a maybe good sleep. Is that clear?
Yes, sir.
Okay, thanks. So look at the algorithm once again, and also now you notice the flowchart. So if you look at the flowchart, we take the network, initialize. When you are initializing, what you are actually doing is submit X, then fix your epsilon or the delta, whatever it is. The connection weights, then compute the activations. Right? When you compute the activation, of course, for the step 0, it is your initial inputs itself will go, but for the rest of the iterations, you calculate the activations and check the stopping condition. Okay, when you are checking the stopping condition, you check if there is a if winner is there. Okay. Now let me go back to the algorithm. Few minutes back we said winner is identified using two approaches. Now tell me how the winner is identified here. How the winner is identified in this particular this one.
Sir, whatever has positive activation, provided that other all have zero
No,
activation.
no, Akhil. We have seen two types of calculating the winner few minutes back. Now tell me how winner is calculated for MaxNet.
Sir, I think it's dot product.
Yeah, it's dot product, right? It's a, if you
Yes,
look
sir.
at,
Yes.
it's simply dot product. So the winner is calculated, right? So winner is through dot product. That is, what is that? Net input. Now tell me. Now tell me something I said while talking about calculating the net input. What was that? While talking about this one. How do do you take minimum or maximum?
Sir, maximum.
So that means, so when you are taking the net input as the criteria for selecting the winner, you look for max net. Okay, and that's the reason why. What is the network name?
MaxNet.
That's all. So that's all is the max net. What I suggest is, shall we have to solve the book back exercise or would you solve it?
Sir, we can try one in the class itself.
One in the class, then we can try.
Okay. So, okay. So let us take one, this one. Let us take one example, right, the class. So, we have a problem in the book. It is given as this. Imagine you have a network. Okay. So imagine you have a network with 4 neurons. Okay. The 4 neurons are A1, A2, A3, and A4. Excuse me. And the connection weight epsilon. Okay, don't worry whether it is lambda or epsilon. Its connection weight is given as 0.2. Okay. Initial activations are given. The inhibitory weight is also given. What we do is that first we have to, we also know the activation function, right? We also know the activation function which we discussed in the previous slide. So let us do the step 0 or first iteration. Okay. So first iteration, what we are doing? Okay. I think the values have to be given. So initial values A1 is equal to 0.3, A2 is 0.5, and A3 is 0.7 given. A4 is 0.9. The initial activation values are also given. Now what we do is that we proceed by presenting these values to the network and calculate the first iteration. So you regard this as A1 0, A2 0, A3 0, A4 0. These are the values. Okay. Now we are going to calculate A1 of 1. Okay, the net input. So A1 of A1, that means the first neuron for the first iteration, the activation would be A1 at 0, and the summation of epsilon into summation of your rest of the all other nodes, right? So take an example, k is equal to you should not put 1 here, but k is equal to, for k not equal to j, you iterate ak of 0. Okay, so that means what we are going to have is 0.3 for the A1 node. So the 0.3 minus epsilon is 0.2 into, what we are going to do is that we are going to have the activation, because remember, for the step 0 we just pass these activations, right? So step 1, what you are going to get is the output from step 0. What is the output from step 0? The input that is given at step 0. So that is 0.5 plus 0.7 plus 0.9. So what is the value you get? Net input to the what is the value you get? Somewhere around you get, okay, since the value is there, somewhere around you get around minus 0.12. Okay, and remember what we got is the net. Now we have to apply the activation function. So the activation function, as per that, it's not a positive activation, and hence the output, the activation, that what you get is 0. Is that clear? Is that clear?
Yes, sir. Yeah.
So now this is the activation, the output what you get at the second node. Now calculate for the first node. What we calculated is for the first node. Calculate for the second node. So for the second node, A2 of 0 minus all this sigma epsilon into sigma AK0, right? So you calculate this, what you get. So here A2 0 is 0.5. So that means this is 0.5 minus epsilon is 0.2, and the output from the rest of the nodes. So rest of the nodes, that means 0.3 plus your 0.7 plus 0.9. Right. So the activation would be positive. So the value that comes, you get about 0.12. Okay. So the net input is positive, and the output would be, since the net input is positive, the node passes the same net value as an output. So you get 0.12. Similarly, do it for third node and do it for fourth node. Okay. So with this, your one iteration is completed. So what is the stopping condition? What is the stopping condition we need to check?
Sir, if only A2 is 0.12 and all other 0, then that's the stopping condition.
Yeah, if because remember we have not actually calculated here, we do not know A3, A4 are going to give you 0 activation or some other positive activation. If you are going to have A3, A4 as a 0 activation, your A2 is the winner node. Now, you just look at the input and tell me what could be the winner node.
Sorry, A4.
Yeah, so we need to iterate it. We need to iterate it. It takes about 4 iterations. By the 4th iteration, you will see that all other nodes, that means A1, A2, A3, A1, A2, A3. So this is check. Okay, A3, A4. So check stopping condition. Go to second iteration, third iteration, fourth iteration. So somewhere around 4th iteration or a 5th iteration, what happens? One among these A1 to A4 will have positive output and rest will be 0. So that would be the winner. Once you have that, what we do actually is whether the network is converged or not, we iterate it for one more time and ensure that the pattern is continuing. If the pattern is continuing, means network is converged. Okay, is that clear? Is that clear? So this is a very simple network where what we have done, of course, we have taken a very simple example also. The point is you have linearly arranged nodes in the network. Then there are interconnections among the nodes having fixed weights. Look at the algorithm. Is there any parameter or the point where we are actually modifying the connection weights?
No, sir.
There is no modification, right? There is no modification of weights. So when you are doing the second iteration, what we are going to do is we are going to keep this 0.2, the epsilon value, the connection weight value, the same as a constant. There is no change in the connection weights. Okay. Third iteration, fourth iteration. So the network proceeds like this and gives you the values. So please continue that. There is a other exercise also in the book. Please try to address that exercise problem so that you will understand the network behavior. Then this would be helpful when we proceed further while solving